My name is Alex, and in the last few weeks I've finished up the 3D design of the robot, printed everything, and assembled. You can see this is the final design. These holes are for time-of-flight sensors, and let's remove the legs so we can see the insides better. This top bowl is for the soil, and it has some holes for the wires for the sensors that go into the soil to go into the main body of the robot. And now if we remove the outer sleeve, we can see the inner core of the robot where all of the electronics are housed. This is the power side. It contains the power converters, PD triggers. This is where the power banks go. And this side houses all of the microcontrollers, some of the sensors, and all of the sensor connectors. Additionally, the final board was soldered, connecting all of the microcontrollers, Raspberry Pis, and the sensors. Additionally, I wrote the inverse kinematics code to make the legs of the robot follow specific paths, and we were able to demonstrate our robot moving during the demo day.
Hello, I'm Henry and I'll be walking you through the power system of our robot. First, the power banks and the rest of the system all slot into the robot's core here. These power banks then transfer power through our custom USB-C cable. These connectors are E-marked, which allow for the high power flow. The VCC power line is also fed through an ACS 712 for current sensing and an INA 226 for voltage sensing, allowing us to coulomb count and estimate the battery's state of charge through some of the code running on the ESP's 32s. These cables then plug into PD triggers, which demand the 20 volts for the full 100 watts of power from each power bank. However, this is then stepped down through these buck converters to 5 volts, which is what the majority of the robot runs on.
Hello, my name is Alina, and together with Petrula, I've been working on the sensors for the project, so monitoring the plant's conditions and helping with movement and navigation. So the final I2C devices which we've used in the project are a GY271 compass module to tell the robot which direction it's facing relative to magnetic north, like the angle, and also return a cardinal direction. We have used 6 time-of-flight sensors, VL53L0Xs, to return the distance between a robot and any surrounding object, and let us know if it's too close to anything, and so it won't collide. We've also used a VML7700 light sensor to return the light intensity and measure total daylight hours, and an SI7021 humidity and temperature sensor to monitor the temperature and humidity of the plant.
Hi, I'm Petrula, and through the past few weeks I've been working on the sensors for our team. One of our main focus was to integrate UART-based sensors. This included the DPS module and the soil sensor. For the DPS module, our main goal was to extract accurate location data in order to navigate PodBot. The soil nutrient sensor was interfaced via an RS485 to TTL converter, allowing us to communicate over UART with our ESP32 and getting information about the plant's health, such as the pH, soil moisture, nitrogen, phosphorus, and potassium.
Hello, my name is Keegan, and I'm going to go through what I've been doing for the past 5 weeks. So we've just made a few changes. We've added a lot of files to basically work the main controller on the Raspberry Pi. I'm involved with the Raspberry Pi as a central control node and how it connects with all the other facets of the project. The main things that we've added is now we've fleshed out the full database system. So it's got the preloaded plant profiles, the alert system, robot backups, and also sensor historic data. I've also added a weighted function for the weather forecasting, so it pulls weather data from the API, and based on these parameters, it scores them using a weighted function and compares scores with other locations around the robot to autonomously decide where to go next. So that's what I've been doing.
Hello, I'm Natalie, and I'll walk you through the new features added to the mobile app. On the summary screen, additional metrics are now displayed. Users can switch between time ranges, and each chart supports more data points. Charts can also be expanded or collapsed to help focus on individual metrics. An alert screen has been introduced to show unresolved plant issues. Users can review and mark alerts as resolved. The app also sends notifications for new or recurring alerts, keeping users informed without needing to check manually. The new location screen displays the robot GPS position on a live map. It updates regularly and is useful for tracking movement across larger areas. Another key update is the integration of IBM Waternik's Assistant. The chatbot now understands natural language even with typos or informal phrasing, and can respond with relevant information. Finally, the status screen provides a summary of the robot's current session, showing the robot ID, selected plant, and battery level. It also includes an option to start a new session when needed.